Okay, so I want to spend a little bit of time talking about uh, strengthening mechanisms today, right? And those of you who, was anyone in here in that physical metallurgy class? Last year, yeah, Ben here. So this is sort of that was sort of an abridged version of is uh, what was seen here, but this is just sort of classical metallurgy, right? What are the interactions, right? So we'll get to slip and twinning right after, twinning and martensite right after the exam. That will wrap up our crystalline plasticity part of the course. But if we just think about slip, right, we have dislocation carriers, and we already discussed a little bit how dislocations can act with other dislocations to act as sort of pinning points to give us a square root of the dislocation density dependence on the yield strength, right? But there's a whole plethora of other things that dislocations can interact with, right? So we've got, secondary phase particles, grain boundaries, voids, right? We have inhomogeneities with respect to concentration, right? There's a whole sort of plethora of obstacles in the material that defects can interact with, right? And some of these are, if we step away from metals, right? A vacancy or an interstitial can be a very strong defect, right? Why? Because we throw off our charge balance, right? Remember, in crystals, in ionic crystals, dislocations carry a net charge, right? And anytime you have an electrostatic obstacle, like an interstitial or a vacancy, right, that is another dislocation obstacle. So all of these things sort of conspire together to strengthen the material. So it's, for this reason, we have a couple general rules, right? An alloy is almost always going to be stronger than a highly pure metal, right? A well-annealed metal with a large grain size and lower reduction defects is always going to be weaker than a cold-worked metal, right? A alloy that contains precipitates will tend to be stronger than a solute solution strength alloy. Right? There's exceptions here, right? But these are the general sorts of trends. So the theme of the day here, right, is that the strength of any crystalline material is going to be increased by obstacles that restrict dislocation. Anything we can do to reduce the dislocation. So what if we go back to some fundamentals, right? We have the Orwan equation. What does it say? Right? The shear rate is going to be proportional to what? The number of mobile dislocations we have, right? So the plasticity carriers times the velocity of the dislocations, right? So if we can reduce the velocity, we reduce our the shear rate for a given stress. Right? Or if we remove our defects, we're going to reduce our shear rates. So if we consider obstacles with some effective spacing L prime, right? What do I mean by effective spacing? Well, so as we'll see when we talk about weak obstacles, the actual spacing between the defects might not be the actual distance between the pinning points, right? So we have this effective strength L prime, and if we go back and we look at our Orwan-Boeing equation, right, we're going to the obstacles are going to bend between the obstacles until they reach some critical extrusion angle and they break through. That critical extrusion angle could either be for looping, right, or for shearing of the particle, right? The particle is not strong enough. So this obstacle strength directly determines the flow stress. So if we have strong obstacles that we can't easily cut, our critical theta angle goes to 0, and we go around the defects, and our effective defect spacing is actually the distance between the particles. If we imagine what happens, right, our dislocation line is going to come up, and it's going to hit these particles and stop. So I'm going to hit these particles and stop. And so even though the particles aren't in a perfectly straight line, our dislocations will bend, so it's essentially touching. All right? And so in this case, our maximum tau is going to be GB by L roughly. Right? As our theta critical goes to 0. Yeah.
Tau is weak. Tau strong would be there's no tau strong.
What's that?
P phi c is 0, then it is tau strong, right? That's the first thing. That's the tau weak.
Yeah. So as phi goes to 0, right?
Yeah, that's for strong obstacles.
That's for strong obstacles. I haven't talked about weak obstacles yet.
But you think for strong obstacles, the other cause.
Well, yeah, but here theta critical is small for strong. You'll see for weak it has a different form, right? So for weak obstacles, right, the dislocation doesn't get stuck at all the defects, right, at all our pinning points, right? It remains basically a straight line because it can cut through these particles fairly easily, right? It can move through those particles fairly easily. So as the dislocation line lays straight, L prime is significantly larger than the actual particle-to-particle separation, right? It's the lineal intercept approximately between the particles, which means that our critical angle basically approaches pi. We don't have a significant amount of bowing, right? And that basically we end up with, for weak, we end up with the same factor, but now we've got 3 halves here, and our phi critical is about pi, is approaching pi. Right? So we've got something small raised to a power greater.
What's the assumption behind this equation?
What's that?
What's the assumption behind this equation?
It's I'd have to go back through. It's Friedel's sort of derivation of going through, but he basically starts out by saying if we let pi go to phi, this becomes our L prime. right? It is going to depend on the angle and the actual distance.
You don't have square root.
There's a square root here. This is to the 1/2, right? And then I don't remember the exact derivation of how it gets to, how it comes up with 3/2 here, right? I'm sort of just presenting this without derivation. I can go back to the original Friedell's reference and work and look through the derivation for you. But basically, the main idea is that I want to capture is that when the obstacles are weak, the dislocation line remains straighter, right? And you don't have you're not relying on bowing to go around. And so this becomes an important balance when we talk about precipitation strengthening at the end of this lecture, because as the particle size changes, right, if our volume fraction of our solute remains the same, and these are precipitates, as our precipitates age and grow, they get larger, but if the volume fraction of solute stays the same, it means our spacing is also going to get bigger because some particles are going to dissolve at the expense of others, right? And so that's greatly going to affect the balance between bowing and cutting, right? Because we're going to be affecting our separation and our effective length and how easy the particles themselves are to cut. So the dislocation structures that result will be very different depending on the age state of your precipitation hood. Right. Okay, so back to just a refresher, right? For the most part, when we're talking about work hardening, a work hardened material or dislocations as obstacles, we're really talking about this stage 2 sort of regime, right? If we just think about work hardening, I mentioned Cottrell's comment about turbulent flow. Maybe I did. Anyway, so Cottrell, in his famous paper from 1953, basically said that turbulent flow is widely considered the most difficult unsolved problem in physics. In my opinion, it has nothing on work hardening. And he likened early glide to a laminar flow regime, and stage 2 and stage 3 hardening to the transition to turbulent flow. And he says, unlike in fluid dynamics, we don't yet have the concept of a Reynolds number to parameterize this transition from one mode to the other. Right. So defects can either act as hard or soft obstacles, right, or strong and weak obstacles, depending on the other neighborhood, right? So if we think about dislocations, other dislocations that lie in the same slip plane, right? So if we have two parallel dislocations that come together, if they're of like sign, they're going to be a repulsive effect, right? But is that a strong obstacle or a weak obstacle? It's going to be pretty weak. The stress of a pileup is fairly small. It's not. But if we have dislocations that are running at a angle to the slip plane, right, that are cutting across the slip plane, right? Now when these defects interact, they're going to leave a jog, right? So that's what we call forest hardening, right? and that's a much more strong obstacle than defects that lie in the plane. So dislocation intersections produce hard obstacles. Multiple slip in polycrystal and later deformation in single crystals leads to a set of immobile jogs, right? Which we then have to get around either by bowing or extrusion, right? We talked a little bit in the last class about how we get the row 1/2 dependence. I assigned it as a homework problem a couple of years ago. That did not go well. But anyway, so tau naught here is the intrinsic strength of the material with a very low dislocation density. What's going to basically determine tau naught?
Elastic modulus.
So the modulus, right? So that's definitely goes in there. G is the shear modulus. And this is basically the Peierls barrier and any other intrinsic defects that are in the material, right? This is how easy these defects are going to be to move, right? The lattice friction plus any, say, grain size effects, right? How likely we are to hit obstacles other than other dislocations. Right? So in a single phase alloy, tau naught is basically just a function of the lattice friction. And then there's this alpha factor, right, which is different for FCC and BCC. And this basically accounts for the fact that we have different populations of dislocations with different intrinsic mobilities, right? So in hexagonal, it tends to be even higher, right? Because the C plus A type defects are not nearly as mobile as the prismatic or the basal defects, right? So the same reason that gives us a stronger temperature dependence of yield on BCC and HCP versus FCC also gives us a stronger degree of strength. Different defect populations. Yeah.
How do we estimate relative mobility?
What's that?
Like for alpha equal to 0.4 in BCC,
Yeah.
that's the system without different mobility.
Yeah.
But relatively we cannot estimate that.
Well, you can by modeling, right? It's difficult to do experimentally. You can look in the early stages of deformation and look at the rate of evolution of defects, right? So you can see what dislocations are actually present. Right? Your probability of observing by TEM.
But that will be different on the system. Different elements will have different.
Yeah. Yeah, different defects have different relative mobilities. It's not something we can easily measure, right? These geometric factors are largely empirical, right? This is just fitting. There's no fundamental physics that goes into determining these factors, right? It's just the different populations of different defects are a rationalization as to why, or a physical picture of why they're different, right? It doesn't allow us to calculate. And so this square root behavior with this different dislocation densities is observed over a really huge order of magnitude of defect population change, right? So here, I mean, this is super low, 10 to the 10th, right? This is like the most carefully grown single crystal ever, right? Kind of levels, right? And 10 to the 15th, this is highly work hardened polycrystal, right? And you see a pretty good relationship, which tells you, right, that we basically go from a 2 order of magnitude change in our yield strength, right? We go from 1 MPa for easy glide in a single crystal to 100 MPa at the end of stage 2 hardening of polycrystal, right? So that's pretty significant change. So we talked about this before. I'm going to come back to this sort of after. I'm going to hit some details here. But what I want to do is, with today, with the exam coming up, I just sort of want to hit a couple highlights of this right now, and then go back and get a little quantitative after the exam. Otherwise, we're going to miss some important things. Okay, so grain boundary strengthening. Everyone's familiar with the Hall-Petch effect, but why does grain size give us a affect our yield strength, right? And we can basically have a simple model of a polycrystal, right? And each of these are different orientations, right? Our stress field is not homogeneous, right? It's not even homogeneous within a grain, right? You can imagine if you have if this is a plastically hard grain and this is a plastically soft grain, or this is a grain that's well aligned for slip and this one isn't, right? We still have to have stress equilibrium and compatibility, right? So we're going to have a different stress at this side of the grain from this side, right? But if this is a plastically soft grain, we're going to activate slip, right? We activate this slip system, and we have some Frank Reed source here, and we get a pileup, right? This pileup comes with the stress concentration. This is a plastically hard grain over here, right? So it needs a much higher critically resolved, it needs a much higher stress to get to the critically resolved shear stress to activate a defect source here, right? But basically what happens is this pileup has a stress concentration. So the more this grain deforms, even if our macroscopic stress isn't changing, we're altering the stress state in this grain. And eventually this pileup stress concentration becomes large enough that we can activate this source and we get slip in this grain, right? So basically the smaller the grains, right, or the larger the grains here, the more slip we can have in this grain to activate sources near the neighbors. Right, so that's sort of a physical picture of Hall-Petch. Right? And we see that a very strong we see big differences in the Hall-Petch coefficient. The amount of the grain size affects the yield strength. Right? BCC tends to have a much stronger Hall patch than FCC, and HCP is also much stronger than FCC. So the high alpha values that we see out front also contribute, that we were just talking about, also contribute to the Hall patch. Okay. Solid solution strengthening. Right? Dislocations interact with other things, in this case solute atoms, to give rise to strengthening. Right? So if we have a dislocation here, right? Here's our slip plane, we have an edge dislocation here, and we're moving towards this, in this case, a small solid atom, right? Above the slip plane, are we in a state of tension or compression? The atoms. All right, the atoms are squished. Below the slip plane, we're in a state of tension, right? Atoms are farther apart from them. So what happens as this small solute, the core of this dislocation, comes in contact with this, in proximity to the solute? Is that going to, is that a favorable energetic configuration or an unfavorable? It's favorable, right? It's going to relieve some of that compression, right? So in this case, the dislocation is going to be attracted to this solute atom. What happens if it was below? Right? The dislocation is going to be repulsed. The same way, if we have a larger solute atom above or below, right? If we have a larger above, we're going to have a repulsion. If we have a larger below, we're going to have an attraction. Right? Okay, but here's the rub, right? These solute atoms, these don't move around very fast, right? Those have to diffuse, right? If it's an actual substitute solid solution at room temperature, right? There's not a lot of mobility for these to hop around. So the scale of the deformation, we can assume that these are sort of fixed. So our dislocation doesn't start out near here. Our source can be well away, right? So our source doesn't know that this solute atom is here, right? So basically, there's no preferential probability as to whether this solute atom should be above the slip plane or below the slip plane, right? Right? Should happen with equal frequency. So why don't the attractive and repulsive effects just balance each other out and give us a net zero strengthening?
Yeah. Doesn't it strengthen in both cases?
It does strengthen in both cases. Why though?
In both
You
cases,
should know this because this is the second time you've seen this.
Yeah, in both cases, it prevents it from moving.
Yeah.
It's locked in both cases.
Yeah. So let's be a little more sort of physical about that, right? Dislocations aren't fixed to remain straight, right? They can curve, right? So that means the dislocation can sort of choose where it wants to be, right? So if it enters an attractive zone, right, it's going to want to stay there. If it approaches a repulsive zone, it's not going to want to be there, right? So it's basically going to be in its lowest energy configuration around these obstacles. So you're always going to have to give it a push to either break it away from the attractive region or push it through the repulsive region, right? So you get strengthening from both cases. Both the attractive and the repulsive give you a benefit. Okay. So for a screw dislocation, it's pure shear. There's no dilatational component. So screw dislocations don't have a size effect with solute defects, right? The screw dislocation doesn't care about the size. Right? Only the edge component. Only the edge component. Right? So that's a little out of order. I mentioned before, we'll call these spherical distortions because essentially the effect of this substitution, right, gives us a stress field around it that's a sphere. Right. We can have asymmetric distortions, such as a vacancy in ionic crystal, or an interstitial in BCC, right? Carbon and steel and iron, right? And this gives you instead of just a hydrostatic stress state, this gives you a triaxial stress, and these are much stronger interactions than due to the stress field than just the spherical. Plus, they interact with screw dislocations, right? Whereas a substitutional atom doesn't. So these are hard obstacles. Okay. So we'll be a little quantitative about the magnitude of the size effect, right? And we work through some derivations. But we also have a modulus effect, right? Why would the modulus of the substitution of the solute atom come into play? What's that?
It depends on the G.
Depends on the G, right? Right. What's our rule of thumb for dislocations? The energy of a dislocation, GB squared, right? So if we affect the shear modulus, right, in the realm of in some local area, we're going to affect the energy of the dislocation that goes there, right? So the energy is proportional to the shear modulus, right? So if a substitutional atom is more compliant, we are going to be attractive, right? If the substitutional solute atom is stiffer, the dislocation is repulsed. So just in a warning, the reading is confusing. He says hard and soft, right, meaning more and less compliant. So he ends up with weird language in there saying that a hard atom is a weak obstacle and a soft atom is a hard obstacle, right? So just be a little careful when you're reading through, and when he's talking about modulus effects, replace hard and soft with stiff and compliant, and then it all makes sense. Okay? So again, we'll look at it sort of quantitatively. But we can see that when we have a more compliant solutes, our energy is additive, right? They're both the same signs. We get a much stronger effect than when we have a size difference with the stiffer atom, right? then they still add, but they have opposite signs. And you weaken your overall. So the best bang for your buck is a largest possible size distance difference with the most compliant strengthening. So what's roughly the biggest size difference that we can get? What's from sort of our Hume-Rodley rules, right? If we get too big of a size difference, it's not going to be a single phase solid solution, right? It's going to phase separate. So what's a rule of thumb for the biggest that we can put in?
15%.
About 15% size difference, right? So okay, and then so that's the overview of the solid solutioning. Now we have secondary phase particles. Right? So particle sizes. What's our gold standard for sort of particle strength? Right? What do we really want? We look at precipitation hardened aluminum alloys. What are we going for with processing? What's going to make it harder to bow around? Right. Yeah. So we want a very small spacing, right? So ideally we want a very fine dispersion of secondary phase particles, right? So that we're going to have very tortuous paths, right? If we have widely separated obstacles, right, it's our effective spacing becomes too large, right, and we're easy to get around. Right? So for, say, processing aluminum alloys, we're really looking for a very fine dispersion of particle sizes in the sort of nanometer regime. Right? Very, tens of atoms to thousands of atoms. Very, very good at promoting hardening. Okay. So we have a couple effects that we need to consider. Right? If we're going to, we have a particle there, we need to think about the coherency of the interface. Right? So perfectly coherent interfaces, if there's a lattice mismatch between our particle and our matrix phase, right, we're going to have a coherency strain. Right? Dislocations are going to interact with the strain field. Right? If we have a incoherent interface, dislocations are going to come in, and then what? Right? It's hard to move a dislocation through an incoherent interface, right? Just like a grain boundary. Very difficult to move a dislocation through a grain boundary because you don't have any atomic matching, right, through your interface. So this becomes very difficult to cut. This is easier to cut, but you have a strain interaction, due to coherency strains. Then you're going to have some defects, some interfaces that are semi-coherent, right? Where essentially you have rows of edge dislocations that you can use to model your interface. So we've got a different set of interactions going on there. Right? So we can think about the strain field and the volume mismatch. Right? We also have a modulus effect. Right? If we're cut into a precipitate that has a different modulus, now the energy of the line energy of our dislocation is changed. as we go through, right? So that gives rise to another effect, right? Then if we shear a particle, we're also making new interface. Every defect that comes through, we create a step, right? So that means we're creating new interface. So the interfacial energy of this, right? We have to pay a penalty to create the energy. We call this chemical strength. And then we have order strengthening, right? So imagine we have a stacking sequence A, B, A, B, A, B, right? And this dislocation comes through and we're sheared over by one vertex vector. Now we have a stacking fault, right? So we have to pay the penalty of the stacking fault energy to shear through that, right? This gets quite complicated when we think about ordered compounds, right? So in nickel-based superalloys, our full FCC dislocation is a partial superlattice partial dislocation in the gamma prime phase, right? So we have all kinds of different faults that can happen because what happens now if we have a partial FCC, right, that enters, right? Now we need multiple combinations of different partials, and we have a whole host of different stacking faults that we can create, right? I'm not going to be so worried about the details of that, but this order strengthening concept is really can be really quite important, right? And so those are all the effects of cutting through particles, right? As the particle gets larger, we're not going to be able to cut nearly as well, right? Right. So then we're going to bow around, right? And then we're back to Orlan bowing. So the general trend is going to be as we get larger, it's going to be more difficult to cut, right? But bowing becomes easier, right? So the maximum strength is going to be right where they're equal, right? You've got a monotonically increasing function and a monotonically decreasing function, right? Your optimum value is always going to be at the intersection, right? So the best strengthening we can get in the system is going to be right when cutting and bowing are balanced, right? And this is our sort of what we call our peak age configuration, right? Where our particle size distribution is ideal to give us the most possible strengthening. Now, if we have a different system where, say, the cutting increases, the ease of cutting increases then decreases because of interfacial things or other aspects, then our peak strength is not necessarily going to be an intersection, significantly lower, right? But if this were to monotonically increase, this deficit is what we want to try and minimize. Okay, so that's sort of the 10,000-foot view of strengthening. After the exam, we'll go through sort of the equations, and we'll be able to go through that fairly quickly because sort of the concepts are in place, especially if everyone has a chance to read the chapters that I'm going to put up between the exam and the following Monday. So on Monday we'll go through this with some detail, and a week from Monday we'll go through this with some detail. This coming Monday is basically question time, right, and review. I won't be posting a solution to the practice exam, but I will also take questions on those on Monday. Right, and that should give you a good sense of what I'm going to be what I'm going to be looking for.
When will it be posted?
What's that?
When will it be posted?
This Friday. And it's compared to previous years, I want the exam to be a little more conceptual and not just so much problems, which I think will make everyone happy, I hope, right? But make sure you have a calculator that you can do eigenvalues, eigenvectors, right, of at least two, right? One quick point, right? You're going to have something. Right, you're going to tend to see tensors that look like this, right? Because now I know right away that sigma 3,3 is an eigenvalue and 0, 0, 1 is going to be an eigenvector. And so that means I only need to solve a quadratic for the determinant instead of a cubic equation. I only need to factor a quadratic equation rather than factoring a cubic equation, right? So I can do tricks like this. So if you find yourself trying to find eigenvectors and eigenvalues of a general 3, right, you've probably done something wrong, because I want this to be, any problems to be easily doable by people who don't have a calculator that can do these things, right? I don't want someone to have to take half an hour to solve an eigenvector problem by hand. So if you find yourself in a situation where you're really chugging through some crazy math, it means that you're either missing a really simple way of doing it or you've made a mistake. Right? So we'll stop a couple minutes early today and make up for all those times I was 5 minutes late, right? In previous ones.